All right, welcome to our last lecture of BC Calculus. As we discussed, it's going to be about vectors. Now, as a quick reminder, you can go and copy down all of the notes, all of these filled in things, which you'll see as we keep going, from the PDF if you don't want to keep pausing the video and writing things down, though that, of course, is another option. If you have any questions that aren't answered by rewatching, obviously put those in the comments below. A timestamp can be really helpful for that, and I will answer them as soon as I can. So let's get started. So we're going to talk about vectors today. Now, a vector is a mathematical object. So that just means it's a thing that we do math with. So like an equation could be an object. And a vector is a mathematical object with both magnitude, so magnitude meaning length or force or size or strength, and direction. So you'll often see it written like this over here. You've got -4 and 3. Those are the horizontal and vertical components for a vector, which would look often like an arrow. And you've got a horizontal component this way, x, and then a vertical component, y, and this vector would be written as x, y, like so. Now, if we have to find the magnitude of a vector, remember magnitude means length, we're going to rely on our old friend Pythagoras. So here we see a vertical and horizontal components. And so what this means in this case is that if I start at a point, the horizontal structure, horizontal component tells us we go -4, and so we're going this direction because it's negative. And then +3, so up 3, and our vector in between them, this is not great to scale, but it's close enough. This would be the vector, maybe we'll just call it u, of -4, 3. So as you can see here, we formed a right triangle, and if we're looking for the magnitude of the vector, which is written as the absolute value because we're still talking about a distance, this magnitude then is going to be equal to, as I said, the Pythagorean theorem. You can also think about it as the distance formula of your x squared plus y squared, -4 plus 3, which in this case is 5. So the magnitude of u, or the length of u, is 5. Now, the derivative of a vector, you'll notice they're still written as component forms, is you can treat this almost the same way that you would treat a parametric equation, where you have your function of x and you have your function of y. It's just written in a slightly different way. But for the most part, it acts in a similar fashion. So here we're given the position of a particle moving on the xy plane, and we have our vertical and horizontal components, where y is a twice differentiable function of t. At t equals 1/2, what is the acceleration of the vector? So here, since we are given position to begin with, and we're being asked for the acceleration, all we're going to need to do is find the second derivative of each, meaning in this case, x double prime and y double prime. And I'm using this configuration because it's asking for a vector as a final answer. So in this case, we can use our knowledge. We can find the velocity vector first. For the first one, we're just going to use the product rule, bring the 3 down, and we get 12t squared. And then for the y, we're using the chain rule of y prime of 2t times 2. And acceleration would be the derivative of that. Bring the 2 down, 24t, and y double prime, 2t times 2 again, and then the original 2. So you might say that your acceleration vector in general is 24t at 4y double prime of 2t. Last thing we need to do here is that the t's in this case are equal to 1/2, which gives us our answer here of 12 for the horizontal component and 4y prime of 1 for the vertical. So speed of a vector is where this process gets a little bit trickier. If you recall, speed is equal to the absolute value of velocity, but because we're dealing with vectors, these absolute value signs mean magnitude, which is based on the Pythagorean theorem. And because it's velocity, we've got the derivative, so the derivative of x squared plus the derivative of y squared. So here, when we're given the velocity vector already, great, we don't need to worry about the derivatives in that case, since we're first being asked to find the speed, though we will have to do some derivatives to find acceleration. So in the case of speed here, we are going to take the square root of 2 cosine of t squared plus 3t squared, and you'll notice that there's an x, a y, and sort of a z term. We're talking about a three-dimensional vector. That's just fine. It's going to continue on, of 2 sine of t squared. The Pythagorean theorem absolutely holds in 3 dimensions, and you can simplify this because we're going to end up with a cosine squared sine and a sine squared being added together. We can do some nice simplification, and we end up with 4 plus 9t squared as the general equation for the speed of this particle. Now, for acceleration, because acceleration doesn't have the magnitude or absolute value, we can just take the derivatives of each of those, and for acceleration, the derivative of the first part becomes negative 2 sine t, the derivative of the second is 3, and the derivative of the third is 2 cosine of t. And so again, you can just take each part separately, except for in the case of speed, when you have to deal with the magnitude. Finally here, we've got one where we are given a velocity vector, and we're being asked about displacement, meaning that we're going to have to integrate instead of differentiate. But again, it works very, very similarly. So we'll start by just integrating velocity to find displacement, which, as you can imagine, means that we can just integrate each part separately. So the integral of e sine of t and the integral of 5t squared. And it gives you the bounds here from t equals 1 to t equals 2. And so you can put in the bounds, which is great because then we don't have to worry about trying to do this exponential by hand. Just type it into your calculator. So after typing it into your calculator, you should end up with your component forms, meaning that we have a displacement vector that would look like this, with our horizontal of 2.605 and our vertical component of 11 and 2/3, or 11.6 repeating. Notice here, these are all just numbers, and that's because we're looking for the magnitude, not the displacement vector. So we just need to, again, plug it into the Pythagorean theorem, 2.605 squared plus 11.6 repeating squared, and we end up with 11.954, and the answer here is B. All right, please feel free to leave any questions in the comments that you might have. The timestamp is really helpful, and I will get these back to you as quickly as possible. If you have any questions as well about anything from AP Classroom, I will create a separate assignment for that so that you have space to ask me any of those questions as well. So keep an eye out for that. Thanks and have a wonderful day.